Barbara Rivera joined IDIBELL last October, and as a junior PI at our hereditary cancer group. And she is also an adjunct professor at the Gerald Brockman Department of Oncology at McGill University in Montreal in Canada. This is where she was before she moved to Barcelona. In February 2018, she became an assistant professor at the oncology department to focus her research in the genetics and molecular mechanisms of rare tumors. So now she has begun with us at IDIBELL and to start her own research lines, in particular in rare tumor syndromes. She has very high interest for syndromes characterized by the development of low-grade and benign tumors. So please, Barbara, you can start your webinar. We're looking forward to it. Thank you.
Thank you, Laura. This is my first webinar, so welcome everybody. I hope I can go through this talk with no much technological problems. So as Laura was saying, I've been studying rare diseases or rare cancers for the last 12 years since the PhD. I'm going to talk today about microRNA biogenesis and some syndromes that are associated to defects on the microRNA biogenesis. But first, I want to tell you a little bit, that because the seminar was at the IDIBELL, I tried to make it a little bit personal, and there's some personal touch in it. This painting is from Louise Bourgeois. I know you guys all know her because she's the sculptor of the spiders at the Guggenheim. She was also a painter, and her way to go through problems was to represent them by geographical figures and then reach a solution. That here is this red square. And I find some similarities with what geneticists we do. This is a problem for us, and we represent it with geographical forms, and then we reach a solution, and the solution to this problem, you also know it, is family 1 in the BRCA paper, in the Science paper, where Marie-Claire Kien discovered BRCA1 mutations in hereditary breast and ovarian cancer syndrome, which is one of the most common hereditary cancer syndromes. There are many others that are way more rare and not so well known. One of them is DICER1 syndrome. So the story behind how DICER1 syndrome was described is linked to pleuropulmonary blastoma, which is the tumor that is known as the landmark of this syndrome. Pleuropulmonary blastoma was described in 1988. It is a blastoma of childhood because it appears in children. There's 3 types, type 1, which is a benign cyst in the lung, and type 2 and 3, and the 3 is almost a sarcomatous tumor with life-threatening, very life-threatening. In 1996, our friend John Christ, he is a friend of the DICER community, described for the first time a genetic predisposition to PPBs, to pleuropulmonary blastoma, because there were some families. But it wasn't until 2009 when Hill and collaborators identified that mutations in DICER were responsible for these familial PPB syndromes. In those families, there was also other type of tumors. There were, in particular, Sertoli-Leydig cell tumors, which are tumors of the ovary, non-epithelial, of the sesquiosomal, sesquiosomal tumors of the ovary. So, who is DICER? You know, but I'm going to do a very brief introduction on DICER. DICER is a processor of microRNAs. It cleaves a precursor of a microRNA and into a mature microRNA that will get further loaded into the RISC complex and then regulate transcriptional regulation. Okay? So DICER, this is just a scheme view of DICER, and this is the hairpin. So this will be our precursor of microRNA. It has 2 enzymatic domains. RNase 3B that cleaves on the 5', and the 3A that cleaves here. And these little balls here, they mark residues that are metal binding, and they're key on the enzymatic activity of DICER. The phenotypic spectrum of DICER syndrome is quite wide. Up to date, there's more than 15 benign tumors or malignant tumors or centrogenic mutations described associated to these mutations. This is not up to date, but they mostly affect children or young adults. And the most prevalent alteration is MNG, multinodular goiter. The landmark was PPB. And among those, there are benign tumors like MNG, it's not a tumor actually, it's a novel growth, or very malignant ones like pineoblastomas or pituitary blastoma, they're much rare. In 2011, just before I joined the folks lab, Will and Mark and Thomas described for the first time a gene associated to familial multinodular goiter, and it was Dicer. In those families, there was also presence of Sertoli-Leydig cell tumors, those non-epithelial ovarian cancer tumors I just told you about. And Dicer is still the most important familial multinodular goiter gene, and actually the only one that is bona fide. So I joined the lab in 2011 for a little season, and then came back in 2013 at the same time that this lady, Liane Decoq. And my first task in the lab was to try to find other genes, microRNA genes, associated to Dicer negative families. I completely failed and I didn't find any. So I moved on into different projects. But meanwhile, Liane did a tremendous work in defining new phenotypes associated to Dicer mutations. And up to date, as I say, we have more than 15. Almost everything in blue has been described by Liane. And I mark pineoblastomas and Wilms tumors because there's also sporadic somatic mutations in DROSHA, in another microRNA biogenesis gene, in those two tumor types. So you can see that we're going to start seeing some interplay between genes, mutations, and the phenotypes. This is the landscape of mutations in Dicer tumors from Dicer syndrome, so from patients that they have germline variants, okay? This is also from Liane's work. So Dicer follows a tumor suppressor model with two hits. One, the germline is the one inherited, is a truncated mutation that can be located along wherever along the gene. Most of the 95 or 99% of the scenarios is a truncating hit. These are the representation of all mutations in literature, but they're only represented once, okay? And then the somatic hit, the second hit cluster mostly here, as you can see. So what is here is the RNase 3B domain, one of those domains that cleaves the 5'P, and these residues are in fact those metal binding domains, okay? Or some residues very close to them that affect very much the metal binding. I always go for or try to look in things that I can think of, but I never really pay much attention to what is around. We're pretty focused, right? And I've never really, when I look at the Gioconda, never ever thought that she had a big neck. But a little bit, like a year ago or something, I was looking for a picture for multinodular goiter. And then I found this, and there's some theories that says that the Gioconda had this big neck because she actually had an enlargement of the thyroid gland, that it was the term that it was historically used to describe a multinodular goiter. So multinodular goiter is an enlargement of the thyroid gland. There's a few nodules in the thyroid, and there's these spheres. So I'm not a pathologist, so I don't know how to describe it completely detailed, but this is colloid liquid, and then the cells are here. So there's many nodules within the multinodular goiter. One of my projects during the postdoc was, as I told you, to look into families that were Dicer-like, but there was no alterations in Dicer gene. And one of the projects that I took on was familial multinodular goiter without Dicer mutations. And this was one of the families I studied the most. And as you can see, there's 3 generations with MNG, okay? And there was this man here with thyroid cancer, then this woman with 3 sonomas and 2 ovarian desmoids, and then this kid here had a quarter plexus papilloma, is a benign tumor of the quarter plexus, and also autism spectrum disorder. But we didn't really we thought that the sonomas were just a red herring, and so was the CPP. So I focused on the MNG, and I performed a West study in all of the affected individuals. And what we found, it was a perfect co-segregation with a mutation in a gene called DGCRE. This alteration is glutamic to lysine, and it has never been described in the germline before. We did a big control population, 2,000 people from Montreal, and we also didn't find the alteration. However, Who is DGCRE? Well, DGCRE is the partner of DROSHA in the nuclear microprocessor. So it actually works upstream of dicer. It cleaves a primary microRNA into a precursor of a microRNA that it will get further exported and cleaved by dicer. So it works like dicer, but upstream on the pathway. It does not have an enzymatic activity. It just binds the RNA. So it helps, it's like a docking site. It helps locating the hairpin, the primary, in the proper location. I told you that alteration has never been described in the germline, but then I got all the alterations on databases that have been described in the DGCRE and from publication, and I plot them along the gene. So this is just a schematic view of the gene, a little bit more rudimentary than the ones that Leanne does, but sort of the same. And then I saw this tremendous hotspot here, and it's exactly where the mutation is located, with the same mutation in the family. This, though, is sporadic and somatic. These blue circles correspond to actually Wilms tumors and also to thyroid. There's a couple of thyroid cancers here. These pink ones are PDTCs. The mutation is located in this helix that is key for the binding of the RNA. So see, in Wilms tumors and in a couple of follicular variant of a PDTC, this mutation was a hotspot. So now this is how the family looked at the end of the project. The project finished last year. And from that family with only MNG, we passed to a family that had MNG in all these 3 generations, but also schwannomas in him, her, and those 3 kids. She, as I told you before, she had 3 schwannomas when we started, and we thought that there was just a red herring. But as of today, she had 9 peripheral schwannomas. All of them are peripheral. He had also had peripheral schwannomas and those 3 kids too. And this is just the study at the tumor level. So this is a wild type allele of the glutamic acid in 518. This is the lysine. And as you can see, most of the tumors or tissues, MNG, this is the CPP, had LOH at the position. Okay, this MNG didn't present the LOH, but I think it was the only one. We did in silico prediction of the alteration. This residue helps stabilizing the helix that binds to the RNA and stabilizing this other arginine, and when you introduce a lysine, those hydrogen bridges, bonds, they get broken or disestablished. But who is DGCRE? It's not only a microRNA processor gene. Its name comes from the George critical region 8, and it's located in the 22q11.21 region, which is that region. It's the one that is microdeleted in 22q11.2 deletion syndrome or the George syndrome. And it's also right beside LCTR1, SMARB1, and NF2. And what do these genes have in common? Well, they're key genes in the development of schwannomas, and in particular, peripheral schwannomatosis. For just very briefly, for those that are not familiar with schwannomatosis and the term, is a genetic disorder defined by the development of multiple peripheral schwannomas, benign tumors of the one cell, in the absence of bilateral vestibular schwannomas, and is characterized by either germline hypomorphic mutations of SMARB1 or deleterious mutations in LCTR1. These are the 2 key papers. So schwannomatosis also follows a tumor suppressor, but there's not only 2 hits, there's some scenarios in which there are 3 or 4. I'm gonna show you the most plausible one. There's other possibilities, but first hit will be a hypomorphic mutation of SMARB1 inherited. If you inherit a completely deleterious mutation of SMARB1, what you develop is an ATRT, and it's a rhabdoid tumor of the brain. So this is a hypomorphic mutation. Then the second hit will be an LOH. You lose the other allele of 22 of the chromosome 22. And then there's a third step with an NF2 mutation back in the allele where the first SMARB1 mutation was. So those will have 1, 2, 3, and 4 hits. You can have the same with LCTR1. One deleterious LCTR1, LOH, and then a further NF2 somatic hit in the germline LCTR1 carrying allele. However, because in LCTR1, SMARB1 is located in the middle, when this LOH happens, you also delete one allele of SMARCB1. So there's some theories to say that this is 1, 2, 3, 4, and even 5 here. So we wanted to test the tumors in our family because schwannomas are not linked to Dicer. So we needed a way to know if these schwannomas are related really to DGCRE alteration. So we first look at, this is a genome-wide analysis. This is done with West of whole genome data. We analyzed some of the tumors by West, of whole genome, others by SNP arrays, the MNGs, because the quality of the DNA was much lower. So just you see this chromosome 1, 2, 3, 4, 5, up to 22. Okay, and here I have the germline representative of one individual in the family, and then his tumor, the germline and tumors, germline and the CPP. And here for those PTCs, I told you there were some PTCs described on the TCGA, yeah, on databases, and I got them. They were at Biobank in Toronto, and we were so lucky to get them. So as you can see, the genomes are quite stable. The CPP has some movement here, some rearrangement, which is normal. But then when we look at chromosome 22, the germline, it's all centered in the middle, which means there are heterozygous calls. Each dot is a call for a heterozygous SNP. So when those calls, they go to the edges of the allelic plot, then we have homozygous call here, meaning there's an allelic imbalance or a loss of one of the alleles, okay? So all of the tumors in the chromosome 22 had this loss in the 22. Okay, so then we said, what does DGCRE does canonically? Well, microRNA cleavage. Let's test the microRNA profile of these tumors. So Javad was my partner in crime on this. He is a very talented bioinformatician working at McGill. And we're reading mature microRNAs. Okay, so our readout for now will be mature microRNAs. This is a nanostring profiling, so it's an array of microRNAs. And we put together FBPTC, so papillary thyroid tumors, with and without the mutation, MNGs, here by color, with and without the mutation, and schwannomas. And we clustered them. This is unsupervised clustering, hierarchical clustering. As you can see, all the tumors with the mutation cluster together, and all the tumors without, they go together. And they cluster together independently of their tissue of origin. So the mutation is overreading here the tissue specificity of the microRNA profiling. Okay, good. So this was positive. So then we said, okay, let's validate this with a different subset. And because that particular mutation was a hotspot in Wilms tumors and the data was publicly available, we downloaded it and we did the same. Our readout is exactly the same, mature microRNAs, but what we're comparing now are schwannomas and Wilms tumors, with and without the mutation. And the technology is also different. This comes from microRNA sequencing, and the cluster before was an array. Okay, and this is consensus clustering, so it's 1,000 repetitions, okay, of the same clustering. And as you can see, schwannoma, and this yellowish is the Wilms tumors, and then mutated all together and non-mutated on the other side. Again, this is one by one, okay? We looked then at differentially expressed microRNAs that they were in common. There were 190 microRNAs differentially expressed versus mutated versus non-mutated, and they were common between schwannomas and Wilms tumors. And they always follow the same tendency, meaning if it's overexpressed in a mutated schwannoma, it's also overexpressed in a mutated Wilms tumor with the same, obviously, the same. Okay, so then we focus on those differentially expressed microRNAs. And this is a volcano plot. And we look, this is not absolute values, it's relative. We always compare mutated versus non-mutated, okay? Same readout, mature microRNAs. There was a bunch of them that were overexpressed compared to the mutated cases, and some of them that were underexpressed, okay? And I am, one of the top ones was miR30, and I'm marking it here because I'm gonna follow the story towards miR30. What I told you about microRNA processing was valid for canonical microRNA processing. There are other pathways that are not the canonical one. So primary microRNA into a precursor by the microprocessor and then further exported. But we have those called intronic microRNAs or miRNAs that they are located in the introns of coding genes, and they're actually firstly processed by the splicosome and then exported and further processed by dicer. This means they are independent from the microprocessor but still dependent on dicer. Okay, how can we use that input to be more sure about our data? Then what we did is, in the exact same plot with differentially expressed microRNAs in mutated schwannomas versus not mutated, we plotted those miRNAs in black here. So as you can see, all miRNAs, all black dots, are located in the overexpressed part of the microRNA differentially expressed, okay? Meaning that none of them gets, let's say, lacking or underexpressed. And again, this is not absolute values, it's relative. So what matters is that they are all here. Okay, let's go to the Wilms tumors. It was public data, so less depth, so less significant. But again, all the miRNAs located in the overexpressed parts. Well, we were lucky enough to work on a dicer lab. So I told you miRNAs are independent from the microprocessor, but dependent on dicer. So if you plot the same with the dicer tumor, like pituitary blastomas, your miRNAs have to be affected in both ways. And that was our way to validating that the assay was good. And now miRNAs were both in the underexpressed and the overexpressed part of the phenotype. Well, I've been using mature microRNAs at the readout, but the microprocessor works on the nucleus, right? So the closest readout that we could look for are actually precursors. So we try to do exactly the same in the mutated schwannomas and read precursors. The difficulty here is that to be able to sequence precursors, you need a lot of money, because you need a lot of sequencing capacity to be able, because they are quite unstable and they get degraded and they're less abundant. Still, we got 4 mutated schwannomas and 4 non-mutated schwannomas. Again, comparison sample by sample, cluster them separately. And now the volcano plot doesn't look as beautiful, but we were able to reach significance in a bunch of them. Again, miRNAs in black are here, and we have still 3 underexpressed precursors here. And again, miR30. I told you I was going to use miR30 later on. And we wanted to further validate all this in vitro. And to select one precursor, we thought, okay, which one is common between the precursors and the mature microRNA, so we can be sure it is the defect on the precursor production that leads to the downregulation of the mature microRNA, and also is common between stop differentially expressed between the Wilms tumors and the schwannomas, and that was miR30. So we use it, and then Maria, who was a postdoc at Will's lab, and now she's a researcher at the Navarra Biomed, she's super talented, did this assay. It's an in vitro cleavage assay. So what you do is you feed a primary microRNA with the sequence for the miR30 into a complex, you radio label it, and a complex with wild-type DGCRE and DROSHA, and also wild-type DROSHA, but mutated DGCRE. You incubate it, the reaction has to happen, and then you incubate it 0, 30, or 60 minutes, okay, for both of them. And what you see here, this is the primary microRNA, and in the wild-type complex, you start seeing a band in 30 minutes. The size is 65 nucleotides, which is the size of hairpin. Of this hairpin is around 21 to 22 per each, plus the loop. Okay, in the mutated, we didn't see any. So at least in some, a subset of precursor microRNAs, the defective DGCRE is not able to do. All right, so what happens when you have a defective processing of microRNAs, where your precursors are low, your mature is low, and then your target mRNA doesn't get inhibited and then goes up. Okay, what are the mRNAs that get overexpressed in this schwannoma? So we compare the same, but now what we're doing is total RNA sequencing, mutated versus not mutated again, and now what we're looking is on the other side of the graph, right? So among the top 10 overexpressed RNAs, there was KRAS and NRAS. This obviously doesn't prove causality with miR30, but it's true that they are targets of miR30. We need to do experiments in vitro to assess what kind of role this overexpression has, if any. But it is true that there's some links in the literature between RAS pathway and multiple schwannomas. There's this girl with diffuse schwannomas and a rasopathy and a mutation on KRAS, a German mutation on KRAS, not the typical D12, but in residue number 6. And there's also some peripheral schwannomas with KRAS or BRAF alteration. Obviously, LCTR1 is a Noonan, doesn't only cause schwannomatosis, but also cause Noonan syndrome, just different alterations in LCTR1, and it has some regulative role in the RAS pathway through ubiquitination of RAS or RIG. There's some controversy, so it could be possible. So I told you the path to schwannomas in the most septic one, in SMART1 or LCTR1 through a 2, 3, or 4 hit model. So what could be the path of schwannomas from DGCRE? So we will have one mutation, that is upstream of LCTR1, and then we evaluated a total of 9 schwannomas with this mutation so far, and all of them had complete loss of the entire chromosome 22, and then half of them had a wild-type NF2, and half of them had a 4 and 5 had a mutation in NF2, I think, or 5 and 4, something like that. In those, they retain an unmutated copy of NF2. In a couple of them, we had enough protein to do Western, and Merlin protein is there. So we know it's NF2 wild type. So what we're looking now is, are there other phenotypes associated to DGCRE? Obviously, I was very eager to find new families and new cases. We know schwannomas and thyroid nodules or tumors. And then we're asking collaborators, if you happen to know of a family, please let me know. About families or patients with schwannomas and thyroid nodules or tumors, and maybe Wilms tumors, pineoblastomas, CPTs, choroplexus tumors, papillomas or carcinomas, and ovarian tumors. And because I was coming to the IDIBELL, one of the first places I looked for, obviously, was here at the hereditary cancer program of the ECO and the IDIBELL. And I asked Joanne, and they had 3 families, candidate families, and I sequenced them. And then in this one, this guy had 7 schwannomas, MNG, papillary thyroid cancer, and a renal cyst. And bingo, he was a carrier of the same mutation. And now Elia is the genetic counselor working with this patient. So what we would like to do is try to write the path, the same path that has happened in the last 10 years for mutations in DICER. These are all the phenotypes associated to DICER. These are the phenotypes that we know for now associated to DGCRE. Maybe there are more. Maybe there are some that are not tumors. We don't know. We know that somatically it's mutated in Wilms tumors. In fact, it's the most recurrent mutation in Wilms tumor found, that particular E518K. And complete deletion of DGCRE has been seen in pineoblastomas. Pineoblastomas are weird, and they can tolerate complete deletion of one of the microRNA genes, which none other tumor can tolerate. But maybe there's a DiGeorge syndrome, or we don't know, or other phenotypes. We will keep working on that. Well, I'm going to change gears now for the last 7 minutes or so of the talk, and I'm going to get out of the syndrome. I'm going to talk about tumors, but I'm going to talk about thyroid in particular. So thyroid tumors and its implication in DICER with DICER mutation has been increasing more and more in literature. I can thought a few papers about DTC, and particularly in children, in adolescents with thyroid nodules or DTC and frequent mutations. The rate of mutation for this study was like around 16%. This is a plausible model for development of MNG in DICER syndrome. So you get one truncated hit, germline, will lead to a hyperplastic thyroid. This is just a supposed model. And then a second hit on an RNase, and then you get hyperplastic thyroid cells with that driver hit. And there's a clonal expansion, and then you get the multinodular code. And then we look obviously in TCGA data where they sequence 400 PTCs. Let's see if in public PTCs there's dicer mutation. From the 402, there's only 2, so 0.5% of cases with dicer mutation. It didn't even make it to the figure. This is the typical landscape of mutation in DTC, most associated obviously to MAP kinase pathway. But still, when you work on a rare disease, it's key to have numbers, right? And very hard. And because the thyroid is the most prevalent alteration in Dicer syndrome, I was very interested to learn about the gene by analyzing thyroid lesions. So then we had this colleague, Yuri Nikiforov, in Pittsburgh, who has developed this amazing clinical testing screening. It's called ThyroSeq, and it screens for more than 200 genes in total nucleic acids coming from fine needle aspirate of thyroid nodules. That is the way of screening for thyroid nodules. And it combines with cytology, and it gives you risk and so on. And it tests both fusions and driver alterations, including the hotspot mutations of Dicer. So we decided to go for a new study. And this is the results of Sophie, is a master student at McGill, supervised by Will and myself. And we started with almost 15,000 thyroid nodules that passed through ThyroSeq, okay? And then from those, we found a mutation in Dicer in 214. So this is already 1.4% of thyroid nodules with a mutation in Dicer1. So from these guys, we selected those with a concentration of total nucleic acid of more than 2 nanograms per microliter. This just is what allows me to do the assay that I wanted to run. That was a total of 61. So then we chose 61 age, sex, and cytology match of non-mutated Dicer thyroid nodules by ThyroSeq. And we perform an analysis in duplicate with an array that screened the entire coding region of Dicer. 59 samples here at the end and 61 here. And we did everything in duplicate, okay? And then we went through a very strict filtering, and we're not gonna go through these steps. I can explain you later if you want, but the important is that 76% of those samples with a hotspot mutation in Dicer had another truncated hit. So following those 2 hits I told you before. And none of the ones that had a hotspot negative samples had any hit. So by screening those hotspots, you're capturing everything. But what is even more important is some of these will be germline. Yes, they are. We have a subset of them that we have normal tissue, and actually some of them are germline. So that is very important for the management of the patients. This is the plot of all the mutations that Sophie did. Those are the hotspots here, and those are all the duplicates along the gene. And this is obviously somatic because we did it on the thyroid nodules DNA, but it resembles a little bit that germline model I explained you at the beginning. And then Sophie went further. We unblinded the results of the ThyroSeq for other drivers of thyroid cancer, and we plot them. And those are Dicer1 mutated cases, and those are wild type. And those are all the other drivers that had mutation in these cases. As you can see, they are exclusive, or they tend to be exclusive with Dicer alterations. So these are thyroid nodules, which tend to be most of them benign. And the percentage of alteration was much higher than in DTC by the TCGA, than in differentiated thyroid cancers. So Dicer1 seems to be implicated in less aggressive thyroid lesions, but is this universally true? Well, poorly differentiated thyroid cancer, it's intermediate form between differentiated and very aggressive and differentiated thyroid carcinoma. And the 10-year survival is way worse than in PTC and in differentiated thyroid cancers. This data is from models, but it's very rare in young persons, in young individuals. This is a study from my friend Inigo Landa, and he studied adults PDTC, a series of 81, and only one had a mutation on Dicer, and that woman was actually a case with 22 years old. So obviously Dicer never made it to the main figure. What happened in young persons? Well, they're very rare. There's around 50 in the literature, and we got 6 of them with less than 21 years, and we passed them through ThyroSeq, and there was nothing in any canonical driver of thyroid cancer. So we performed West in tumor and normal pairs, and I'm not going to go into the results of that for the sake of time, but from the 162 known cancer susceptibility genes, DICER1 was the only one that had mutated in 2 or more cases. We know at the beginning somatically, but then when we perform the West, even one of them is germline, and these had 2 hits, and this also had LOH, so 2 hits. We didn't have enough DNA from this, and there's only 1 case that didn't have anything in that. So no is not only present in benign thyroid lesions, and that represents again a problem for managing the patients. So to sum up, DICER and DGCRE are both MNG susceptibility genes. MNG is the most frequent manifestation of the DICER syndrome, and by the age of 40, the cumulative incidence of MNG or thyroidectomy for thyroid nodules was 75% in women and 17% in men. MNG is always more frequent in women. With DICER1 compares to 8% and 0% in controls. 1.4% of fine needle aspirates from thyroid nodules have hotspot DICER1 mutations, and 75% had also a loss of function variant, and they're exclusive with non-oncogenic drivers of thyroid cancer. DTC is increasingly recognized as a characteristic feature of DICER syndrome, and DGCRE might also be implicated in a small part of papillary thyroid cancers. And DICER1 is implicated also in aggressive adolescent onset, poorly differentiated thyroid cancer. And identifying these patients with DICER1 mutations and thyroid nodules is important, not because of them, but also because the wide spectrum of alterations linked to DICER syndrome and the management of their kids or their relatives. And this was the Fox Lab. Will was my mentor during 8 years. Most of this work has been done, obviously, there. This was my little team at McGill. There's tremendous number of collaborators, and this is my new team. And also the girls, Hirim came with me to Barcelona, and Clara and Aida joined the lab, and all the funders. So thank you to all, and to all of you.
Thank you, Barbara. That was a very beautiful study where you've identified a new gene for this tumor predisposition, whether benign or not, but it's tumor predisposition anyway. And also all the this second part of the talk about DICER1 in thyroid nodules. So you are talking about genes involved in microRNA biogenesis. And when I think about it, I think that the effect should be very strong because microRNAs are involved in the regulation of so many genes. And if I think that this is altered in the germline, I would either think, my first thought would be that this would be embryologically lethal, or if it's not, the phenotypes would be very severe. However, if you look at the pedigrees and the tumor types, it doesn't seem to be the case. I mean, it's not as aggressive as one would have expected, no? You've even found germline mutations in the thyroid nodules, no? That are just causing probably these benign alterations. So what is your thoughts about it? And do you think that maybe it's these 2 proteins, DICER1 and DGCRE, that are not so essential, that there's something else working there? And that's why we don't see germline mutations in genes such as DROSHA or other genes that maybe are more relevant to the microRNA biogenesis.
So first of all, if you delete them completely, they are embryonic lethal, each of them, Areté, DICER, and DROSHA. Then it's quite interesting. When you can have a truncated allele in the germline, but DICER, DROSHA, or DGCRE, they're highly regulated themselves and their expression. Okay, so obviously, only from all tissue types that we've seen so far on the tumor types, and the spectrum goes beyond 15, only pineoblastomas can tolerate complete loss of one of them. Why? We don't know. Pineoblastomas are weird. The rest, they need a germline, and the other is a missense mutation. The missense mutation in those RNA, in those metal binding domains, obviously they shift the microRNA production, but they probably don't shift it completely. There are microRNAs that are independent from DICER. They're processed by Argonauts. and they're microRNAs that are processed by dicer but independent from the microprocessor. So you probably play one or the other. Also, not every microRNA that gets loaded is the 5p. That is the one that gets not cleaved if you have a dicer mutation in the 3b. Having a dicer mutation in the 3a is completely, there's one that is actually seen with enough prevalence. So I just think that it has to be the good one. Now, you cannot be a fully germline of those RNase 3b mutations. Those kids can only exist as a mosaic. Well, maybe there's one, and he is severely, severely affected. That is fully a germline of those RNase 3b. DGCRE is the one that has the less effect by far, because it doesn't have any enzymatic activity. So Drosh still cleaves. It's just that it doesn't cleave properly. I didn't show you more data because of the sake of time. This doesn't cleave properly, but it still cleaves. Why don't we see germline mutations in Drosha? That's an interesting point. There are somatic ones, and we know, hasn't been published, that there are a couple of families around the world with germline mutations in Drosha, and what they have are phenoblastomas, because are the only tumor types they can tolerate. That's all I can tell you, but I wish I had more info.
No, that's good. Yeah. When you did the thyroid nodule study, where you tried to look for DICER1 mutations, you found several with mutations, and then 75% around that had a second hit in DICER1. Yeah. So you said this was important because many of those were, the first hit was germline. So this was important for the counseling of the families and relatives. I mean, these people many of them probably don't have much aggressive phenotypes. Would you recommend screening relatives, the carrier relatives, or how is that? Because it's the study is just random. I mean, it's not selected for family history or anything. So it was first of all, we don't know the real percentage that is German, because the study was pretty much to know, okay, let's see if by screening only the hotspots, you catch everything. You don't need to screen the entire genome dicer. That was the case. But let's still see if the two hits get confirmed by having an actual tumor set or a sample set that is super big, because you don't get to do this with pituitary blastomas. There's 10 around the world. Mm-hmm. So that was great. But it was a retrospective study. We didn't have normal. It's blind. We don't know. Some of them will be germline. Why we know that? Because we had 4 cases extra that we had tumor normal. And in those 4 cases, 3 of them had a second hit, so 75%. 1 of them had a germline mutation. So it's only 1, but at least we know that some of these people will have. It's just so the second part of the study now, this study is finished. Sophie's writing the paper. The second part, it goes about that and about which mutation comes first within the thyroid nodule to drive the nodule. Genetic counseling, for sure, is just the prevalence, both the prevalence and the penetrance is very different depending on the phenotype and the age. When you're old, you're at risk of Sertoli-Leydig cell tumors and thyroid nodules, and that's it. It's for the kids mostly. Okay, very interesting.
I think we can leave it here if no one else has any questions. So thank you very much, Barbara, for giving this fantastic talk, and everyone for joining today.